Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 4 CS2594D. So we would like to show our data set, which is we choose electrical grid stability simulated data as our data set. So this is our group members, which is we have Muhammad Hadri bin Yus Nizam, Anas Amsyah bin Ayub, Hibri Dayan bin Hisham, Isha Hazmi bin Shamsul Kaha, and me, Zuhasri bin Azlan. So this is our introduction, which is our introduction is modern power systems are becoming more complex and dynamic, increasing the risk of electrical grid instability. Monitoring and maintaining grid stability is crucial to prevent blackout and equipment damage. This project applies a backpropagation neural network, which is BPNN, to classify the stability status of an electrical grid using simulated sensor data. Next is our problem statement. The dataset contains simulated sensor readings representing electrical control parameters in a power grid. However, real-time classification of grid instability status is not readily available. This project aims to develop a model that can accurately classify the grid condition as stable or unstable, enabling faster decision-making for grid operators. Lastly is our objective. First, our objective is to build a classification model using the backpropagation neural network algorithm. Second, to pre-processes the electrical grid dataset for training. Third, to evaluate model performance under different training configuration, which is epoch and data split. And lastly, to assist in automatic detection of unstable grid states.
Assalamualaikum. My name is Irshad Hazmi, and I will be talking about our dataset overview. This dataset overview is to tell the general information for our dataset. So the first one is the data source. Uh, this dataset contains of 10,000 samples with 11 predictive variables, which is four of them is tau x, and three of them is px, and four of them is gx, and one unpredicted variable which is p1, and two goal fields which is f dot step and step f. We can see the variables after this, and next one is each samples are involved in reaction time, nominal power, and coefficient proportional to price elasticity. So the next one is features. The first one is reaction time of participants. This mainly for the tau x, which is this for the value for electricity producer from where 0.5 to 10 seconds. Next one, nominal power. This is for the px, which is consumed negative, produced is positive. The next one is coefficient. Gamma proportional to price elasticity. This is mainly for the Gx variables, which is the value for electricity producer from range 0.05 to 1 seconds, power of negative 1. Okay, next one is the target for our datasets. So the target is the stability, which indicates if the system is unstable or not. So the binary output is 1 or yes equal to stable, or 0 or no equal to unstable. So this is the binary classification problem. So the next one is the data pre-processing. This we need to apply normalization for all input features to ensure efficient gradient descent. And we need to use binary version of the target for the classification problem. And if there is missing values, we need to handle them. And the last one, we need to make sure our data is clean to do pre-processing, like data partition, for the splitting of the data. Okay, this is our data sets. Uh, from number 1 to 4, we have tau x, which is tau 1, tau 2, tau 3, and tau 4. These types is the continuous types, and there is no missing values. And the next one, we have px, which is p1, p2, p3, and p4. P1 is the unpredictive variables, and there also is the continuous types and no missing values. Next one is the gx, g1, g2, g3, and g4. This is also continuous types and no missing values. And we have two goals, which is steps is the continuous types and no missing values, and step f is the binary type, and there also are no missing values.
So next we're going to system architecture, which is a backpropagation neural network. So first of all, we need to download our CSV file from UCI and then import it into Python, like this one. Next, we need to build the neural network using import numpy. Next, we'll evaluate test set using sigmoid, and then it will show the epoch and the loss. Lastly, we will test our accuracy of our model. We got a test accuracy of 0.6535.
Assalamualaikum and hello, my name is Mama Adri. Now I want to tell you about model training. First, we have three hyperparameter when we use to model training. First, we have learning rate. We use 0.1 and 0.2 learning rate to so this learning rate will we will train the model. And second is the epoch. So the epoch is how much the training model took. We use 50 and 100 training model. And lastly, we use training testing percentage splits, 70-30 split and 80-20 split. So what is the training model? Training testing split. So this is a common for 7 and 30 split is a common split that you have a medium to large dataset and want more data for testing to get a reliable estimate of model performance. Okay, so for the 80-20 split, in often it used when you want to maximize training data, especially with smaller dataset, while still keeping enough for performance evaluation. So we have model evaluation. So what it do, it measure how well the train VPN produce on unseen data, and it help determine whatever the network has learned the correct pattern or it just memorizing the pattern itself. Lastly, it detecting overfitting or underfitting. So overfitting is a model when it's learned the training data too well, including its noise and outliers. This leads to high accuracy on the training set but poor performance on new or unseen data. For underfitting, it is too simple to capture the underlying pattern in the data, resulting in poor performance on both training and testing data set. We have 7 items for method to model evaluation. We have accuracy. It's how it's predict how many prediction were correct of all test sample. Precision of all predicted positive, how many were correct. So recall is out of all should positive, how many the model correctly found. Everyone score is to a balance between precision and recall. So recall is how many actual sample belong to each class in test data. Macro average, average of score for each class. Treats all class equally. So weighted average, take class size into account, show overall model balance. Now we want to see a 730 split testing and 50 epoch training model. Okay, this is a result for testing 0.1 learning rate. So the epoch we can see in the table how much the accuracy is and loss, and the training average we know the value we can see in the table. It have a value for training average for precision, recall, F1 score, support in the stable, unstable, accuracy, micro average, and weighted average. Okay, for 15 epoch for 0.2 learning rate. For the table, you can see the training, how much the training accuracy gets, and losses in 50 epoch. And training average, you can see the value of for position, recall, F1 score, and support in the stable, unstable, accuracy, micro average, and weighted average. Okay, for second test, we use 730 split and other epoch for our data set. On 100 epoch and 0.1 learning rate we use in the table, you can see the training, accuracy, loss, and in epoch 100. And for training evaluation in the table, you can see position, stable value, recall, F1 score, and support. And you can see stable, unstable, accuracy, macro average, and weighted average value in the table. For 100 epoch and the 730 split test, we and we use 0.2 learning rate in the table. In training you can get training accuracy, loss, and at the 100 epoch. And for training evaluation table, you can see precision, stable value, recall, unstable value, F1 score, unstable value, and support, stable value and unstable value. Precision accuracy value, precision macro average, precision weighted average, recall accuracy value, recall macro average, recall weighted average, F1 score accuracy value, F1 score macro average value, and you can see all at the table training evaluation.
And then next we have 80-20% split, learning from 8,000 test science samples and 2,000 test samples. Uh, like now, uh, it will be run for 50 epochs and a learning rate of 0.1. Uh, it's stable. The classification report shows the stable results are stable, accuracy, macro average, and weight average. The training continues with using 0.2 learning rate with the same 50 epochs and 80-20% split. Uh, and it shows again stable, unstable, accuracy, macro average, weight average. Next, we have 80-20% split and 100 epoch. Starting from 0.1 learning rate, training evaluation from the training includes all stable, unstable, accuracy, macro average, and weight average again. And then here is the training for 0.2 learning rate for 80-20 split and 100 epoch.
Okay, the another content we have a result graph. For This is a result graph for 7 split and 50 epoch. For 50 epoch training, we use 0.1 learning rate. This is the first graph. For the first graph is epoch training accuracy. This is, you can see the graph looks like, and the second graph is epoch training loss. And lastly, we have cohesion matrix graph. For 50 epoch, in the 0.2 learning, first you can see how much the difference between 0.1 learning rate and 0.2 learning rate. First, you can see in the slide training accuracy graph and training loss graph. For the graph in confusion matrix, for stable and unstable graph, the difference between 0.1 learning and 0.2 learning rate. Alright, now we want to see the 70 split and 100 epoch graph and how it look like. Okay, for the 70 split and 100 epoch, you can see 0.1 at the 0.1 learning rate. You can see the graph, training accuracy graph in the slide, and training loss graph in the slide. For the coefficient metric graph, how the stable and unstable looks like in the coefficient matrix. For epoch 100 0.2 linear, you can see the how same the in the 50 epoch 0.2 linear is like it's the same graph. For first epoch, you can see how in the slide training accuracy how it look like in the graph, and training loss graph. For the conversion metric graph, and for our output layer, stable and unstable output for the data set.
Next, we have 80-20% split and 50 epoch 0.1 learning rate graphs. It shows training accuracy going up and the training loss going down, and then the confusion matrix for the training. And then for 0.2 learning rate, uh, here is the training accuracy graph, the training loss graph, and the confusion matrix graph. And then next for the 0.1 learning rate for 80-20 split and 100 epoch. Here is the training accuracy graph, and it shows it did at around 90%. And then training loss graph, and then the confusion matrix graph. And then next is the 0.2 learning rate for 80-20 split and 100 epoch, the training accuracy graph, the training loss graph, and the confusion matrix. Here is the summary for all of the training results. Training number 1 with 70-30 split, 50 epoch, and 0.1 learning rate has an accuracy of 94%. 70-30 split, 50 epoch, and 0.2 learning rate is 64%. 0-30 split, 100 epoch, and 0.1 learning rate 71%. 70-30 split, 100 epoch, and 0.2 learning rate 64%. 80-20, 50 epoch, and learning rate of 0.1, 86%. So 80-20 split again, 50 and 0.2 learning rate, 64%. 80-20 split, 100 epoch, 0.1 learning rate, 85%. And 80-20, 100 epoch, learning rate of 0.2 and 60 equals 64% accuracy. The highest accuracy of all the training is the 80-20 split, 50 epoch, and 0.1 learning rate for the dataset, and the lowest are all of the training using 0.2 learning rate.